after the session. Oh, yeah, sure.
Thank you.
Professor, I had a question regarding CPL and LEAP. Which out of the two would be preferred?
Yeah, I'm so sorry that I just cannot. No, I
I have added it in the chat. If that helps.
Which do we prefer, CPL or LEAP? Depends on the circuit. If your circuit if your circuit consists of tutorial variables, then obviously the CPL makes a sense. Otherwise, LEAP is probably the only choice we have. Okay.
And Professor, in CPL, are the PMOSes optional?
I'm sorry.
In CPL, are the PMOSes optional?
CPL does not involve the PMOS. You do use PMOS transistors, but only to pull up the output node.
Professor, in the delay calculation in the class, we discussed like if a internal node is like high impedance or don't care for the transition, we don't use it for delay calculation. But in the review session, you mentioned like if a node is high impedance, we will include it. Like what should we follow?
I will be very specific about that. On an exam problem, I will either give you case where it does not involve high impedance, or I will specifically say include or do not include.
Thank you.
Professor, would you be able to show an example of finding the minimum number of transmission gates given a logical expression?
Sure. Sure. I don't know if this is going to work out at all, but there you go. Okay, here's an expression. What we want to do is, okay, do a Shannon's expansion. Let me do that for everybody. Okay, so listen up, please. What we have to do is take a variable and see if we can actually partition it out. Actually, this is not a good. Well, let me just add a few more things here. Okay, a bar. What the heck? Okay, I just added another term. Okay, so what you do is actually take a variable and partition the whole thing into the variable and complement of the variable. So what you end up having is actually, if we pick out A, it doesn't really matter which one you start off with. Just pick one. And I just like to pick one that shows up on every one of the terms, and it looks like A is on every one of the product terms here. So I end up getting B, C bar, ORed with B bar, D bar, ORed with B, C bar, D. Yeah, that's what goes with A. And then there's A bar, which takes on E. Okay. So if you've done this for one variable, you can now go ahead and try to implement this thing out using just two transmission gates. Transmission gates not looking good. Here's your output. And all you have to do is take A into A bar here, and then take A, and then A bar gets E simply, and then A gets whatever that is in that parenthesis. So how about if we try to do that again, actually, with whatever that's in the parenthesis? This time around, I note that I'm just going to look at whatever that's in the parentheses, and I don't see a variable that shows up on every one of the terms. C shows up here and here, but then B shows up here and here. So I'm just gonna pick random one, and I'm just gonna let it be a B. Okay, B. And it turns out, if you do expand around B, becomes C bar, ORed with B bar, D bar. Oh, no.
Hi, Professor. The third term in the parentheses for A, that's actually B, C bar, and D.
Yeah, so that's messed up. Oops. That's messed up. Let me retype that. Someone equals A B C bar ORed with B bar D bar ORed with B C bar D bar. Oh, not D bar. Is that correct?
Yes,
Yeah.
Professor.
I think so. Okay. So this time around, I want to take whatever that's in the parenthesis, first parenthesis, and I'm going to try to expand around, say, B. Okay. E. And then we have C bar ORed with D bar D. Yeah, I guess that's what. Okay, so and then B bar with D bar, right? So that whatever you see on the second line is actually what's expanded out of whatever that's in the parentheses, and that's what goes over here in the circuit. So I'm going to draw it again. You know, two transmission gates. One of them switched by B, the other one switched by B bar. Okay. And then what you got here, what you got going here is actually just simply D bar. And then what you need to feed here is actually something that we got to expand out again. Okay. But I know from my algebra, this whole thing is nothing but what? Isn't this absorption? You guys remember algebra? What is this? Isn't it just simply C bar?
C bar or D, right?
Is it C bar or D?
It's just C bar.
Yeah, it should just be C bar.
Oh, okay.
Use your algebra, minimize when you can, like what we're doing over here. And you end up getting 1, 2, 3, 4, 4 transmission gates only. You need 4 transmission gates to implement this guy. Okay?
Professor,
All right.
could you do an example like someone previously mentioned where you include, when you're calculating the RC delay, where you include the nodes that aren't necessarily in the pathway, but they're changing? So they were unknown and then they're changing?
I'm gonna skip that. I'm sorry.
Okay.
If a node internally is changing, it's not subject for RC analysis. I mean, if output is not changing, if there's a node internal that is changing, then you wouldn't have to do delay analysis. When you look at a gate, when you look at a module, when you look at anything, okay, you stimulate that with input transition. And if that causes the output to change, then it's gonna matter. Then now we can talk about timing through that box or that gate or whatever. But if the output is not changing, whatever happens inside, who cares?
Yes, I understand that, but someone was mentioning, what was the difference then that you mentioned? The output is changing and certain internal nodes are changing, but some of them were unknown. They mentioned at the very beginning of this
Initial
session.
Z states.
Yes.
I'm going to be very specific about it. So, it's kind of like the problems that we've had in the class or on the exam. We're not going to have a situation where actually we have unknown, initially unknown node. Okay.
So could you do an example of calculating the logic effort?
I'm so sorry. I think my speaker is kind of weak here.
She asked if you could give an example of calculating the logical effort.
A logic effort.
Yes, sir.
Okay. So, the thing about the logical effort, at least for the purpose of what we're going to do with it in the class and the exam, so the difficulty to make a transition at the input of that gate. So let me just give you a random gate here, okay? And for whatever it's worth, I'm gonna just draw a really random looking thing. I have no idea what it is. It's just a monster, okay? And I'm going to say this is the output, and this guy gets connected to, this is what it looked like on the PMOS side. On the NMOS side, it's gonna look like something again, okay? And then I'm just going to actually say, hey, look, these two inputs are connected, whatever, for magical reason. Along with this PMOS transistor. By the way, everything north side of the output is PMOS, right? And it's also connected to, I'm gonna go with this one right over here. Okay, and I'm going to size this transistor as arbitrary as I like 8x, 9x here, 4x, 3x. Okay, and the question is, what is the logic effort for this gate? Okay, so it depends on which input you're talking about. So let's talk about actually the only input that I drew. There must be a bunch of other inputs. What we're going to do is normalize the logic effort with that of an ideal inverter. So that's just 3. And only thing that you need to be calculating is actually the gate input capacitance, and that's the sum of everything that's connected to that particular input, which is 8 plus 9 plus 4 plus 3. Okay. And that gives us what, 24?
Professor, could you please discuss that counter question in quiz 5? Like, how do we get that circuit? I can tell you the sequence if you need that.
I'm so sorry. Which problem?
Design a counter and basically for 0, 1, 2, 3, and then we skip one count. Basically, the count sequence is 0, 1, 2, 3, then 5 and 6. And
How do you
this is a
design
quiz.
this counter, or how do you calculate the? Okay, I will not work on design of this counter. This is 248 problem. Okay. However, I will work with you on dynamic power analysis related to that.
Yeah, we can discuss the power.
Denominator is always 3 for this guy, by the way. Okay? And that's because we're normalizing it against ideally sized inverter input. Okay. Okay, so what is the problem with this sequence? What's the dynamic power of which circuit?
There's a question in the chat. Why is the denominator 3?
I thought I already answered that.
I think it was just
Because
needed to be
we're normalizing everything against ideally sized inverter, which has 3 input or 3 caps on the input.
So it's because there are 3 caps on the input.
3 caps on the input of an ideally sized inverter. Yes.
Professor, do we get any problems on static power calculations?
You may.
Can we do 1 or 2 examples on that, Professor?
Let me try to work on one at a time, please. Okay. So hang on. One question at a time. I don't have multiprocessor sitting here. All right, so what are we getting with this sequence? Are you going to make up a problem that goes with that?
Yes, please.
Okay. I'm going to draw a 3-input NAND gate that's driving another 3-input NAND gate. Okay. And I'm going to say, hey, look, the 3 outputs coming out of this counter is feeding these guys. Okay. What is the dynamic power of this particular node? Did everybody understand the question?
Yeah.
So this is what I'm going to do. I'm going to just write out, actually, let me just type it up. That's the sequence. Okay. Now, next question is, if that's what I'm feeding this NAND gate with, what's going to be the output of the NAND gate? Well, it's going to be 0 or actually 1. Right? It's a NAND, not AND. So I'm gonna get you a 1. Followed by 1, 1, 1, 1, 1. Wow, nothing. Okay. Well, this node stays at 1. It never changes. That makes this problem a boring one. So I'm going to modify it around a little bit. I'm going to turn it into a 2-input NAND gate that is feeding actually another 2-input NAND gate. And I'm going to take first 2 inputs, or the least significant 2 outputs of this counter, and feed it in here and question the same thing. What is the power over here? Well, then I have to figure out what the logic is on the output of this NAND gate. Well, it's going to be 0 or 0, 0. Well, we'll be looking at only least significant 2 bits, right? Okay, I think I messed up. Right here. Makes no difference for this problem, though. Thanks for that correction. And it's going to be 1 everywhere except for this guy. That one's going to get you a 0 now because I'm taking NAND of this 2 guys, right? NAND of this 2, still 1, still 1. In other words, over 1, 2, 3, 4, 5, 6 part periods, this thing flipped only once, and now that's alpha. What are the capacitance on that node? Well, I don't know. I think I have to draw it because I just don't remember offhand. Actually, maybe some of you guys will remember what this is.
Professor, your audio is weak. I guess I don't know. Am I facing the same issue?
Okay, here we go. So I'm going to draw one of those 2-input NAND gates. And size them ideally, it turns out to be actually 2x everywhere. Okay, so what is the capacitance on this node? Well, on the output side, you have 2 diffusions and 3 diffusions for n. That gives us 6 caps. What about the one that goes in? 4 caps. So C equals actually 10 caps. So 10 over 6 CV squared F is the dynamic power consumption. Okay. Is that clear to everybody?
Could you repeat how we got the 10 for C?
10?
Yeah.
I looked at output of this 2-input NAND gate, which is driving actually input of another one of these guys. So input side, of course, we're connecting 1 PMOS and 1 NMOS. That's going to get you 4 C's. On the output side, we get 1, 2, 3, or 6 C's from the diffusions. Okay.
Okay, that makes sense. Thank you.
Is it 10 over 6 V squared F instead of 10 over 6 C V squared F?
The C is just a constant, so you can leave it out if you like.
I just thought the C was the capacitance.
Yes, it is. But it's just a big constant we've been talking about, actually. It's just some big number. So that every time we talk about, like, you know, 1 capacitance here, 1 unit, it means actually 1 C here, 1 C here, 1 C here, and so on and so forth.
Professor, I had a question in regards to calculating alpha.
Well, someone asking, how can we get 0 when you have 0, 1, 1 on the output of this counter? Well, I just drew it in for you. Okay. What about alpha?
So just to like give an example, if the outputs were like, I guess 1 0 0 0 0 0, to calculate the numerator of alpha, do we consider the like when it goes, or yeah, if it like cycles back and it resets to 1, so after the last step, yeah, right there,
Yeah.
would that count as, okay, so because it goes from 1 initially to 0, and then after it resets it goes back up to 1, and that, okay, cool, thank you so much.
Well, let's get to the next question. What was the question?
So will we get the logical effort calculations for high Q and low Q gates?
We didn't really delve into low skew, high skew. I did mention I don't think it's very important. I want you to understand the fact that you can actually bias the gates so that they become differently skewed, or have different duty rates. But then I'm just not going to put that in the exam.
Okay, thank you.
Next.
Professor, can you do problems on static power calculations?
Static power. I'm gonna have to get that. Yeah, here you go. Here's a static power in a nutshell. Okay. There's a superficial leakage, gate leakage, junction leakage, contention, current. These are the sort of main things that we have on this list. Given a technology, we'll have different lists. But given each one of these components, you should be able to just add things up if you're asked to. Okay. Just to know what happens with the static power, it is consumed even when chip is questioned. In other words, when you clock it off, when you don't have any activity on the chip, it will still consume power until you turn the power off. And here's a static power example if you want to go through it. It's just multiplication and summation. Okay, I'm not gonna give you so many different variables to it. But I do want you to be aware of the fact that you have subversion leakage and stack effect. Stack effect is something that we talked about actually. And given the fact that you have current that's related to the VDS drop, the more transistors that you have sitting vertically connected in series, the less VDS drop you will have on the individual transistors. And you can just basically take VDD and divide by however many transistors you got to figure out actually your VDS drop. Okay. So that's That's no,
So not
no big deal.
so basically not transistor will offer less leakage. That's what you are saying, right?
Yeah. That's about it on the leakage. I want you to know subjectively some of the things that we talked about.
So
Next
Professor,
question.
will there be any questions on stack, like any numericals on stack effect?
If I do, I have to give you these expressions, current equations.
Okay, so we wouldn't be expecting.
But I do want you to note things like this.
Okay.
Because it's exponentially related, right? But that's easy to remember. All right, we're like almost there.
Professor, there's another question in the chat. Could you go over a question from homework 3? Give an L model wire driven by an ideal inverter and terminated by a C cap. What is the Elmore delay of 3 segments, each consisting of R and C units?
We did that like 3 times yesterday morning. I'll just do it one more time, okay?
Thank you.
Question asks, hey, you have an inverter, ideal inverter that's driving a 3 segments worth of 1, 2, 3 segments worth of wire that's terminated by 1C. Okay, then each one of the segment is R, comma C, R, C. Okay, so I'm gonna do either one of the 3 models. You want to choose one?
The L model. Or
L model.
Yeah.
Okay. So L model looks like this. We have an inverter. I mean, no, forget inverter. We have a resistor and a capacitor. That's what we get. That's the L model. Okay. How many of this do we have? Oh, by the way, each one of the segment is worth R and C. How many of these guys we got? 3 of them. So we got 1, and then we got 2 like this, and then another one here, and then that terminating end is terminated by actually another C. Okay, so this is C, this is C, R here, and on the driver side, what you have is actually an inverter, which gives you 3 C's on the output node. That's the parasitic effort, right, of the inverter, and it's resistively connected to a source. We'll just assume it's ground. It doesn't really matter. Okay. So what it means is when you pick out a node, any one of those nodes, okay, well, this is a node, this is a node, this is a node, this is a node, we are going to be able to calculate RC for every one of the nodes, just the way it is done on Elmore model, okay? So this guy gets, by the way, this is also R, because it's ideally sized inverter, right? So this guy gets 3 RC over here. And then this guy gets 1 C. There are 2 R's to get to this node from the source. So it's 2 RC. This guy gets 3 RCs. And this guy gets, let's see, 1, 2, 3, 4 R's, but we need to charge up 2 C's. So that totals 8 RC. And when you sum it all up, you get 16 RC. That's the solution. Okay. And then for different models, you just have to substitute in each one of the segment with whatever the segment looks like for that model. Okay. All right. Let's get to next question. What's the next question?
There's a question in the chat asking about logical effort for pseudo NMOS. Will that be on the exam?
Pseudo NMOS. No. I mean, in what technology? For this book? I mean, for pseudo NMOS, I mean, your input's only going to the NMOS side, right? So you should be able to calculate that. And then what would be the, and we're gonna go with respect to actually ideal inverter again. So divide everything by 3. But I don't think I want to put up a silly question like that. Next question.
So there was a question in the quiz regarding why is D flip-flops preferred over a latch? Could you elaborate on that?
It's in the lecture. It's in online YouTube lecture. I also stated it during the lecture twice. Flip-flop, you know how it works. It basically works off of both sides of the clock. Latch is just whatever you give it while your clock is high, it's just going to take whatever that's coming in at the input, and then that is your output actually. And that can cause a race. Race meaning that you have a bunch of circuits here, a bunch of sequential circuits, and a bunch of combination of circuits that your outputs of the sequential circuits are going to drive. And there's a chance that signaling can violate actually. Depends on timing, of course. You can violate a setup and hold. In other words, whatever that's coming in, it's going to change the output, and the signal can just race through this, not exactly once as you would wish, but multiple times, and that could cause a problem. That's race condition, so we don't want to do that.
So, but in D flip-flops, if we do not have non-overlapping clocks, even in D flip-flops, that could happen, right? Race conditions.
If you use latch, it could always happen, yes.
Okay.
Next question.
Okay, there's another question in the chat asking about effort delay, electrical and parasitic effort calculations. Will they be included on the exam? And if so, can you go over an example?
I think I just answered it like about 5 minutes ago. Yes, you're liable for figuring out parasitic effort, electrical effort. Probably for some silly static gate. Okay. And there are plenty of examples in the slide set. So I'm going to skip the examples here.
Yes, sir, in the solutions for quiz 10 that you have provided, I think the answers are not correct. Could you please go
Okay,
through them?
yeah, let me get to that.
Quiz 10, basically the XOR circuit.
Yeah, what about this?
Yeah, XOR circuit is given and the power has to be calculated for an input combination of, shall I tell you the combination or?
No, no. Well, okay. So I'm looking at I can just start drawing things up. We have an exclusive OR circuit.
Yes, sir.
Okay. There you go.
Yeah.
And what
So
what
the
happens at the input?
input combination is 0, 0, 1, 0.
0, 2, then
Okay. Then 3,
uh-huh.
then 2, then 1, 3, and then back to 0.
Okay, and then it repeats. Okay.
Yeah. Yeah.
And,
So we have to calculate the power.
power at the output.
Yeah. So
Do you know what the
alpha should,
capacitance is on the output of the exclusive OR
yeah,
gate?
yeah, it is 12C. So
What? How many C's?
12.
12 C's. Are we all in agreement? Is it like 4 plus 4 plus 2 plus 2? Yeah? Everybody
Yeah.
okay with that? All right.
Yes.
Now let's figure out the alpha. Well, when you take exclusive OR of 0, 0, what is your output?
0.
0. About 2.
1.
One.
About 3.
0. 1, then 0. Or 1 and then 1.
1
Sorry,
and 1,
0,
right?
0, 0. Yeah, last one should be 0, right?
Correct. Right.
I'm sorry.
Which one are really
Did
getting
you
at?
say that gate was a XOR gate?
Exclusive OR.
Okay.
It's just badly drawn. God, I've been making cakes for the past 30 years. And every time I put cake into an oven, this is how it comes out. Anyway, okay. Enough of silly stuff. Let's finish this problem. So what should alpha be? How many cycles are we looking at?
1 by 3.
No, hang on a second. How many cycles are we looking at?
2. 2 by 6, basically. Alpha is 2 by 6. So
6 clock cycles.
yes.
Right? Because it repeats every 6 clock cycles. How many times my signal went up and down, or down and up, don't matter. So it goes up
Yeah,
and down,
two times.
up and down twice, right? That's it. We're done with this problem. The answer to this problem should have been
Yeah, so answer should be 4, correct?
4. 4. Yeah.
Yeah, but in solutions that you have provided, it is 21 by 3.
21 by 3.
So according to your solution, it's 7.
How is it 21 by 3? That's the answer again.
Yeah,
Let me go
if-
back and look at the problem again. Give me 1 second. I'm sorry. We're looking at problem. Please. That's weird. It's supposed to be 4. And the next problem should be what
Yeah,
should be
the next, yeah, the power for next part should also be 4, but it is mentioned 22 by 3 in the solutions.
I think that those numbers are something else. I think I should have checked. Oh, okay. I see. That's a different question. What the heck. I'll get that fixed up. Or actually, I hope it's not. Yeah, but did you follow what we did here just now?
Yeah, we did.
I think that's the important thing. Meanwhile, let me. I see what's happening. I hit Windows 11. It does sorting automatically for me, which kills me.
Are we going to be able to see the homework 3 solutions as well as the quiz solutions?
What is going on here? You know, it's just my laptop's running so slow, and I upgraded to Windows 11, and then it's just messing everything up. Okay. Shoot. Just downward. Why did it pick up this file? I'm sorry. My window thing is stuck. Oh. Come on. This is not stuff. Okay, let me get to your question. I'm so sorry. What was it again?
Yeah, I was curious for the homework 3 solutions. Are those going to be uploaded to the Google Drive before the
Homework
ECEN?
number 3 solution.
Yeah, I was just curious if those are going to be uploaded. That's all.
It should have been uploaded. Oh. Oh. Well, okay. I don't know why it's not visible to me. Refresh. Can you refresh?
Yeah, I see him now. Thank
Yeah,
you.
I replaced it actually. I hope it's the same one. I hope I didn't override.
Gotcha. Yeah, it looks like the correct one.
Because I have another question.
I think there's some kind of corruption here on this folder. Go ahead, ask questions. Yes.
Oh, so if there's going to be domino gates included on the exam, could you just give an example of what might be asked? What might be asked?
Domino gates.
Yes.
I guess plus minuses. How do you draw one? If I give you one, what is it? What gate is it? This kind of question.
All right, sounds good. Thank you.
And of course, along with all the like solutions to make domino work. What is a footer? Why is pre-charging internal nodes, additional internal nodes necessary sometimes? Because charge redistribution, right? Charge sharing problems. Yeah, et cetera, et cetera.
Sir, would you be able to go over the previous example with the XOR gate on or the sequencing and answer? Will there be like an ideal inverter at the end with a cap? Will we always start with an ideal inverter and cap? So not the problem we just did, but the one about a few minutes ago.
Are you talking about the line?
The one with the sequences, like 0000011.
Well,
I think that was asked in the chat a few seconds ago, but I can't remember for certain.
I'm trying to do this back here.
I think that was the one driving wire segments.
The Elmore problem, Elmore delay problem.
The Elmore delay problem? Yeah, we did an L model. Right? Well, Elmore delay problem or the wire model problem. I think, it's in the lecture, just review that out in online thing. There's an online lecture on wire models, right? It's explained out and the examples are done there.
I think the question is, will it always have an ideal inverter as the driver?
No, I could give you something else, of course. And what would matter is actually your internal capacitances, right? And if it's an ideal gate, resistance is always one. But what would matter is actually internal resistance of the gate that's driving the wire. Yeah.
Professor?
Yes.
Can you explain why we need pre-charging?
But whenever you guys speak out, can you please just say something before you start questioning? Like, can you unmute yourself and say, I have a question. Yeah, begin every question with I have a question. Because I get chopped off for whatever reason. First, maybe a few seconds. on my speaker here.
Apologies, Professor. We're sorry about that. There was a
yeah.
question in the chat a few seconds ago. In the problem similar to the ideal inverter driving wire segments, if the driving gate is different, like a NAND or NOR,
Yeah.
how should
Yeah.
we take effective resistance for the gate and capacitance? Will it depend on the
Depends on the gate. Okay. If it's a gate, and then if I size the transistors for you, then you have to actually go figure out the resistance that corresponds to the transistors that's driving it. If I say ideally sized gate, R is always 1. Okay. Only thing that would matter is actually now the capacitance. The reason why you have 3C on the output of an inverter is because your internal capacitance is 3, because you got 2x PMOS and 1x NMOS sitting in there. But if it was, for example, a 2-input NAND gate, then you know that internal capacitance of that is going to be what? How many? 2 plus 2 plus 2, right? 6. So you would use 6. Does that answer your question? So here's your line, whatever the model looked like. Question is, if you're driving this guy with an inverter, that is modeled with 1R, 3C, like that. 3Cs, 1R, right? If you're sticking instead, here's your wire again. If you're sticking instead an ideally sized NAND gate, then what you have is still 1R, but 6 Cs this time around. And that's because the cap at the output node will be 6 instead of 3. And you know why. At transistor level, ideally sizing these guys will get you 2x on the PMOSes and 2x's on the NMOSes. And you're connected to 2 PMOSes and 1 NMOS on the bottom. Okay?
Thank you. There's also another question in the chat. If the input sequence is 0, 2, 3, 2, 1, 2, then what would be the alpha and the power calculation? I believe this is for the XOR gate that we just did.
We just did that here, right here. Right? And that's your alpha right there.
Okay.
Professor, I have a question regarding that wire delay. You mentioned like if the gate is not ideally sized, then which resistance will we have to take, like towards the ground or towards the supply?
It should be the same.
But
Otherwise,
the
I
gate
have
is
to
not ideally
tell.
sized.
If it's just completely randomly sized, then I have to tell you which way. Because it would matter. You will get different R. Depends on whether you're going to VDD or going down to the ground, right?
Yeah.
I have to tell you that. If I say VDD, then you just trace through the PMOS network to figure out what effective R is going to be for that transition.
Okay. And Professor, could you please upload all the solutions for quiz 9? Like only few of the solutions are there.
For some reason,
Professor, I think he just asked if you would upload quiz 9 solutions.
hang on a second. Well, I'm trying to check. Okay. Second part of 9. Okay. Sorry about that. That one I completely missed for some reason. Now it's up. It should be up.
Thank you.
But just to let you know, there's some corruption that went on with the homework number 3 solutions. And I replaced this long file with 3 different files that ends with A, B, C. And those are the correct ones, okay? Sorry about that.
It's no problem. Don't worry about it. We've got another question in the chat. Can you explain the question you asked in midterm 1 about a layout? Like what can be done to make the circuit better?
Oh, okay. So there's only one reason why I asked that question. And it has to do with actually the overall parasitic reduction, or given a gate, whatever the random. Okay, so let me just give you a random example here. If you have A, bar the whole thing, A, B, ORed with C, ORed with D, E. Let's just pretend that this is what we're implementing out. So let's not even talk about PMOS side. Let's just talk about NMOS side. What you're gonna do is like do a straight out implementation that would look like this. Let me finish. It looks really ugly, but you'll know exactly what I'm doing. Yeah, just put A, B, C, D, E, correct? Logically, this is correct, but this is non-optimal.
Professor,
Way
this
to
looks
fix it,
PMOS.
you have to pick this guy and take this guy, swap them. Okay? Because one of the things that I said actually during the discussion was make sure your output or whatever the circuit that's near to the output is lightest. Okay. That way your parasitic on the output is minimized, and so on and so forth. Do you guys remember this pyramid thing? Pyramid deal? What we want to see is the output parasitic minimized, and all the heavier things go near the source, either VDD or ground. So we want to see an implementation solution that look like this. Okay. And when you look at a layout, actually one of the layout was literally, I think it was A, B, or C, or D, E. And you haven't, if I give you a layout that corresponds to this schematic, then it would not be optimal. Okay. If I give you a schematic that look like this, on the NMOS side, by the way, that would be optimal. You can flip this around, that will not be optimal. What you want to have is actually have the output connected to the least amount of parasitic. Okay. Some of you guys were given this, where your correct answer was don't do anything. Some of you guys were given something that looked like this. You have to swap this two. Okay. And I might just give you something that looked like that again. Depends on what I do between now and tomorrow morning. All right, so I'm going to call it evening because I got to get my. Unless you guys have any more questions. Any more questions?
Professor, I do have a question.
Yes.
So I was wondering, in regards to logical effort, do we have to only understand that with just one gate, or do we have to understand multi-stage logical networks? So like the logical effort of a path, kind of like similar to
The
what we
path
did.
effort. Path effort.
Yeah.
right?
Yes.
Let's not worry about it.
All right. Cool. Thank you.
There's a branching effort that comes with it. Right? And these are all sort of simplified methods to sort of, you know, ease our calculation. But these methods work if your circuits are really ideal, or behavior of timing is ideal. And in this day and age, when we have access to simulation tools, nobody would actually employ one of these methods to do back of the envelope timing calculation. Okay, so let's not worry too much about it. All right, I guess I'm going to call it a night. Good luck tomorrow morning. Make sure you show up on time and get well rested. And let's do it just as well or better than the first exam.
Thank you, Professor.
Thank you.
We really appreciate it.